All right, so I'll be talking about this paper that we published about a year ago. It's about the Gaian Bottleneck. That's the name we've given to this idea. And the idea is that the prerequisites and ingredients for life seem to be abundantly available in the universe. However, the universe does not seem to be teeming with life. The most common explanation for this is a low probability for the emergence of life, which one might call an emergence bottleneck. It's hard to get life started. This is notionally due to the intricacies of the molecular recipe. Here we present an alternative Gaian bottleneck explanation. If life emerges on a planet, it only rarely evolves quickly enough to regulate the greenhouse gases and albedo, thereby maintaining surface temperatures compatible with liquid water and habitability. Such a Gaian bottleneck suggests that 1, extinction is the cosmic default for most life that has ever emerged on the surfaces of wet rocky planets in the universe, and 2, rocky planets need to be inhabited to remain habitable. So in the Gaian bottleneck model, the maintenance of planetary habitability is a property more associated with an unusually rapid evolution of biological regulation of surface volatiles than with the luminosity and distance of the host star. So as physicists and exoplanet hunters, we're always talking about the luminosity and distance of host stars, and here we're suggesting that that might not be the most important feature to maintain habitability. And I want to show you a few things about that. So here's Frank Drake, and he writes his equation on the board and says that Shostak took that picture. And right here, these say the fraction of stars. Well, here's the number of communicable civilizations in the galaxy. This is the fraction of the stars with planets, and here's the number of Earths in those planetary systems. So just to let you know that we've made lots and lots of progress with exoplanet findings. Here is 2012. This is a period. This is the mass. Here's the Earth, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and there's Mercury. So that's our solar system. Here are the dots in 2012, and here are the dots in 2015. This is probably the most progress I've ever seen in any field, except maybe for the discovery of the microwave fluctuations in the background. But anyway, this is an incredible amount of progress that we're making. We really are. It's an incredible amount. And we were trying to figure out, well, what fraction of these stars will have planets in the habitable zone? And so we looked at all the multi-planet systems in Kepler, and then we used what is known as the Titius-Bode relation, and we said, okay, let's figure out if we use this Titius-Bode relation, how many would that relationship predict to be in the habitable zone? And we did that, and we said, well, maybe 2 plus or minus 1 planets in the habitable zone. The bottom line is, just because we don't, the selection effect associated with instruments that can detect planets are highly biased towards detecting things that are very close. As you can see from this planet, this idea, it's easier to detect things here than it is to detect things there. But the habitable zone is further away, and so that's what this is. And you can see that these blue dots, which are the detected planets by Kepler, stop more or less here, and then you extrapolate over this pattern, and you get predictions in the habitable zone. When you do that exercise, you get 2 plus or minus 1 planets in the habitable zone. So the bottom line is lots of planets. Now, here is this Drake equation, and you can say that what's important about this equation is it's 0 now. We haven't detected a communicable civilization, and then, well, what's important is you detect 1, you kind of detected everything. If you make a contact with an extraterrestrial civilization, presumably you're contacting a civilization that's always in contact with everybody else. So it's really, I like to think of it as a digitalization. But I'm showing this also because this, look at this, this is the fine structure concept, and he's got it wrong here. It's really upside down. This is the fine structure concept. He has written it wrong. Paul Davies pointed this out yesterday. He says, hey, maybe Fermi's not so smart. It's his comment. Anyway, so here's this equation. These are the astronomical terms which we exoplanet hunters have found good values for. But then there are these other ones tricky that have to do with life. So there's no, apparently there doesn't seem to be an astro-based bottleneck. In other words, we see planets everywhere. So no longer can we say, oh, maybe Earth's a rare planet because there seem to be so many Earths around. Now, Seth Shostak, I added an extra term for him because he thinks that the reason this is 0 is because there's a technological bottleneck. In other words, where our technology is kind of bad, but in the next decade or 2, the technology is increasing so quickly that we're going to find these things for sure. Now, Frank Drake, he has a license plate called N equals L. So this N equals L, and L is the lifetime here. So if the lifetime of a civilization is long, then there'll be a lot. And if the lifetime of a civilization is short, like we probably will kill ourselves in 100 years or 1,000 years, then this is very small. So that's basically everything here is 1, and this is the most important factor, according to Frank. Now, here's one of my colleagues, Simon Conway Morris, and he thinks human-like intelligence might be a bottleneck. Maybe get life is easy, but maybe human-like intelligence is difficult, and therefore this thing is 0. Now, the emergence bottleneck is this term here, and Chris McKay talks about that sometimes. But in this talk, I wanted to mention that we're going to divide this term F-life into 2 terms. We're going to talk about the emergence of life and the persistence of life, and treat those as separate things. You know, this is called reductionism in science. So if this is small, then we have an emergence bottleneck. If this is small, then we have a Gaian bottleneck. And Mark, you okay with that? Perfect. Okay. All right. So here's a picture. Here's a picture of the emergence bottleneck. And let's suppose that here are all the conditions on a planet, and let's suppose that here are the habitable conditions. But maybe you need something more special to get life started. And these are called the abiogenous habitable zone. Let's imagine that these are the conditions you need to get life started. And maybe planetary environments here don't overlap with that. And that would be an emergence bottleneck because the planets don't have a place where life can get started, mostly. And over here, but we also know that planets evolve. So you have a planetary environment here, doesn't have life, and then it just evolves away from habitable conditions. So that would be an emergence bottleneck, the idea that planetary conditions don't overlap very often with the conditions you need to start life. But here's our model. Here are the planetary environments. They do overlap, maybe, often with the place where you need to get life started. But what do? They go, whoop, they evolve away, and then you go extinct. How do you prevent that? Well, it's possible that life, as it evolves, can come up with ways to regulate the albedo, regulate the volatiles, and then possibly maintain these habitable conditions until, of course, you lose all the water, and then boom, we all die in a billion years or so. When people have looked at how long will there be water on planet Earth, there's a mild, tentative consensus that, another billion years or so before we lose the water. In any case, we do know that life has been on Earth for a long time, and the question is, how is that the case? Is it because we're in the habitable zone, or is it because we have life that is actively regulating the environment? So here's a plot we've made. There are 3 plots here. This is time since planet formation. So here's T0, and here's today on Earth. Here's the Earth, here's the Earth, and here's the Earth. Now, one thing about the circumstellar habitable zone, this distance from the star, is that you should know that there's a little bit of history to determining what the HZ, the habitable zone, is. In 1979, this blue line was put there by Hart. Now, for you guys, we've heard a lot yesterday about the carbonate silicate cycle. And that was a paper in 1981, 2 years after this. So here's Hart determining what the habitable zone is 2 years before this abiotic negative feedback mechanism. And he said, look at this. I think the numbers were 0.95 to 1.01 is the habitable zone. And whenever I see somebody who's done a calculation where you know the answer has to be, the Earth has to be there, and it's that narrow, I say, I don't believe that. But then along came Walker, and he said, we have a abiotic thermoregulator, negative feedback mechanism. And then, whoop, the whole thing goes very wide. And so we said, is that really, do we have that type of mechanism working in the first billion years or so? And it relies on subaerial weathering. And that's what really widens this thing up here, subaerial weathering. But then I talked to my Earth sciences colleague, and they said, wait a minute, did we have any subaerial weathering? If we had a little bit of continent sticking up, it was very, very small. The question then becomes, was that negative, abiotic negative feedback sufficiently strong to overcome what we know are obvious positive feedbacks, which make the planet either go really, really cold or really, really hot? So that's what we're talking about. We're comparing positive feedbacks to negative feedbacks and see who's win. And everybody just assumes since 1981 that the negative feedback, abiotic, wins. And that's an assumption we're not willing to make, or at least we're calling into question in this paper. So the idea is, here's like the mean surface temperature. you have all kinds of collisions and bombardments in the first half a billion years. And then most planets either runaway greenhouse like Venus or runaway ice glaciation like Mars. And then occasionally, if you're lucky as a life form, you figure out how to undo or to regulate these positive and negative. You deregulate the positive feedbacks, upregulate the negative one, and we know that life today is heavily involved with what previously was thought to be the abiotic negative feedback carbonate silicate cycle. So the idea is, well, maybe life on Earth got lucky and figured out a little bit how to control that, and then we've stayed alive for a while because of the active regulation of life on the surface of Earth. But most planets, if you get life, they don't figure that out. And then boom, they go dead, cold, dead, hot. That's the idea. And so here are the positive and negative feedback mechanisms. Remember, for the negative feedback, that means it's like a thermostat that's good, it can maintain surface conditions. When it gets too hot, it gets cold. When it gets too cold, it gets hot. That's what a negative feedback is. And the main one that people keep on invoking that's responsible for the entire width of that habitable zone is this one here. And we think that silicate weathering may have been so small in the first half a billion or billion years that it was not significant enough to do what we are claiming, or people have claimed that they can do. Here are the things that we are very confident in, and these are the things that make it go runaway, and these are the things you have to overcome with this in order to maintain some habitability. So if life can get started, we're claiming that maybe you can downplay this and upplay this, and it's the involvement of life in doing that that might maintain the habitability of Earth, and therefore it might be a rare configuration. Maybe most life, when it gets started, doesn't have the lucky mutation that enables it to get its finger on the knob and control the albedos and greenhouse gas content of the atmosphere. We do know that the greenhouse content, the atmosphere is controlled. The volatiles are heavily involved in the biology today. So here's a picture of what the life form on an early planet is like, and then this is what we think happens most of the time. Extinction is the default for planetary life in the universe. And it's an explanation for the n equals 0, or the Fermi paradox, that's a piece of information that you should keep in the back of your head, and this is one explanation for it that is not one of the 75 in Stephen Webb's lovely book, 75 Solutions to Fermi's Paradox. Not yet, maybe his next edition will contain that. So one way to think of this is, don't think of the habitable zone in this way, as if it's a stable equilibrium. Maybe it's like this because of those positive feedbacks which we know are there, making you fall off this way or fall off that way, just like you fall off a horse. And to maintain some nice environment here, you have to actively regulate and increase that possibly very, very feeble negative feedback carbonate silicate cycle. How much time do I have?
1 minute.
Okay, so here's another picture of what, here, maybe life starts everywhere. Maybe life gets started everywhere, but that doesn't mean it can maintain habitability, and maybe all these guys die. And you talk to any biologist, you know that extinction is the default for any species, so why couldn't it be the default for life forms all over the planet, all over the galaxy, and all over the universe? Maybe that's the case. So here's what happened on Earth, and maybe this is what happens everywhere else. One way to test this model is the following. If that's correct, then what will happen is, if there's an emergence bottleneck, like this is the fraction of initially wet rocky planets near the circumstellar habitable zone with life, and maybe this is really tiny. That's the emergence bottleneck. But maybe there's no emergence bottleneck, and then life gets inhabited, and then maybe it just goes extinct, but it lives for a long time. And if there are planets like this, when we land on them, we will see microbes and dinosaurs, big things that are the result of billions of years of evolution. In our model, even if life gets started, we're predicting it goes extinct, and therefore we're predicting when we land on all these planets, we will find no planets with extinct microbial life. Why? Because this is such a short time. A billion years, it's not enough time to make a tetrapod. And so that's basically the model, and that's it.